What's up, everybody? Welcome back to the channel. It's me, Amir here. In this video, we'll be looking at external interrupt in STM32 microcontroller. So an interrupt is a signal that temporarily halts the execution of a program in order for the CPU to respond to some event that can either be internal event or external event. And after that, it will return back to the main program. So in STM32 or in microcontrollers in general, we have two sources of interrupt. We can have internal interrupt that can be triggered by communication protocols like UART, SPI, or I2C. And then we have the external interrupt. So this external interrupt will be as a result of some physical input to the GPIO pin. And if you look here, the first stage, we have the physical input. This infographic will explain how interrupts work in STM32 F411RE to be specific. So in this stage of physical input, what is happening electrically is that we have this pin PA6, that is configured as an input pin with a pull-up resistor. And the importance of this pull-up resistor is that we need to pull the pin to a known state, right? So we can either set it to pull up or pull down, but here we are going with the pull-up. The reason for this is we need to pull the pin to a known state. So here the idle state is going to be 3.3 volt or high, because if we don't do that, then our pin will be floating. And if the pin is floating, it will act as a small antenna. And as a result, it will collect some random electrical noises in form of EMI. And our CPU will interpret this as random sequence of zeros and ones, right? So to avoid that, we need to set the pin to a known state that can either be logic high or logic low. So here we are using our logic high. The idle state is going to be 3.3 volt. And once the user presses the button, then it is going to connect to ground. And that is going to lead to what we call the falling edge. So the voltage here will be dropped to zero. We'll move to the next stage, and that is the external controller. So in this external controller, it is going to do three things. The first thing it's going to do is to map these pins to a specific external interrupt lines. And generally in STM32 F411RE, it has about 23 external interrupt lines. So with the help of this multiplexer, we are going to map this line these are pins PA6, PB6, and PC6 to this external interrupt line. And next we'll have our configuration. And in this configuration, we'll configure the rising edge. Under this edge detector, we'll configure rising edge or falling edge or both, right? But in our case here, we are configuring the falling edge. So this will be responsible for detection of falling edge. And then we have the interrupt mask. And this is a register that will enable interrupt. And we also have the pending register. This pending register gets set when the event occurs. So the sequence that will take place here is if falling edge is detected, then the external interrupt line 6 pending bit will be set. And if it is not masked, the request will be sent to the NVIC. So if you don't clear the pending bit, the interrupt will keep retriggering. And this is why we clear the flag. And it's a very critical step. So the next stage is going to be the NVIC, that is our gatekeeper. And NVIC stands for Nested Vectored Interrupt Controller. So this nested vectored interrupt controller is going to do three different things. First, it is going to group the external line interrupts. And if you see here, we clearly have grouping of these lines. We have line 0 to line 4, that will be for the individual handlers. We also have the lines 5 to 9, that will be for shared handler. And our pin will be under this line. So we'll also look at that later when we configure our project in STM32CubeMX. And lastly, we have lines 10 to 15 that will also be for the shared interrupt request handler. And next in line, we'll also have the priority comparison. If you look here, the NVIC is going to check for few things. First, it will check is the interrupt enabled, and it will check for the priority of that interrupt, and it will check whether the CPU is currently executing something with lower priority. So if all that is valid, then CPU is going to suspend the execution. And then here we also have the context saving. So our processor Cortex M4, it's going to push onto stack the registers R0 to R3, R12, the link register, the program counter, and the status register as well. So this is an automatic hardware stacking. We don't need to write any code for this. Then stage 4 is going to be the CPU and software, where we have the hardware abstraction layer. So what's going to happen here is this vector table is going to map the interrupt numbers to this function address, this function right over here. So that function is usually generated inside some startup file called, I think it's STM32FXXX. it.c. I'll show you that later in our Cube IDE. So, and inside it, HAL is going to call this function here, HAL GPIO external interrupt callback, and then the GPIO pin is going to be pin 6 or whatever pin that we have. But as for this, we have pin 6, which is already here, PA6. And inside it, HAL internally calls another function that is the function now to toggle the LED. So this is step 4. We just say the CPU is going to save registers automatically, and then it is going to execute the interrupt service routine, restores the registers, and continues the main. Can configure our project and start programming. So I'll just head over to STM32 Cube MX. And here I'll just click on Access to Board Selector. In here, I'll just type the part number for my microcontroller. So it's F411RE. Just select the board and start the project. So initialize all the peripherals with their default mode. Here we have our chip. So what I'm going to do, I'll just clear the pinouts. Now, I'll be using PA6 for the external interrupt. So you can see here GPIO external interrupt, that is line 6. We set it, and then we'll be using GPIO pin PA7. That will be for our external LED. So I'll set it as GPIO output. And you should follow this circuit diagram in order to do it. So we can go to the system core, the GPIO, and here we'll have to make modification. So I'll just click on here. We'll have to select the pull-up resistor. And then the GPIO mode is going to be external interrupt mode with falling edge trigger detection. And we can rename this pin. I'll just give it label as a button. And then we can go to PA7. So I think I'm going to leave everything as it is. I'll just give it the name as external underscore LED. So now it's fine. We can go to the nested vector interrupt controller. And you can see here the external interrupt line is going to be 5 to 9. So you just enable this interrupt here. And we can go to the system. So in the system, we have to select the serial wire for debug since I have the ST-Link on board. And now we can go to the clock configuration. And in the clock configuration, I'll just leave everything as it is. And then we can head to project manager. And in the project manager, I'll give the name for my project as external interrupt. And then we also have to select the toolchain or the IDE. It's going to be STM32 Cube IDE. And now we can generate our code. So now we can open our project folder. And then we'll try to open our project using STM32 Cube IDE. So we have our project imported successfully. So I'll just expand this here. And I'll go to the core. We'll have source. And if you see here, we have our main.c file. This is where we'll write our program. And you just go to user code begin. For this is where we'll start writing our program. And I'll just show you another file which I talked about earlier in the video. That's going to be this file. So this is the file where our function is generated, a function address that maps the interrupt numbers. So if you just scroll down here, you see the function is here, right? So we can go back to the main.c file and start writing our program. So here we can write our interrupt service routine code. So I'll first start with the interrupt callback function. So it's going to be external interrupt underscore callback. So we'll have unsigned integer that's going to be of 16-bit. And then we'll have a GPIO underscore pin. So inside this function, we will check to identify if the interrupt is coming from our button. So for that, we'll have another if here. and I'll say GPIO underscore pin is equal to button underscore pin. And if it is so, then we need to toggle the LED. So we'll have HAL underscore GPIO and then toggle pin. So we provide the port that's going to be GPIO A, and the pin is going to be external LED underscore pin. So to make our ISR clean, we need to add some debouncing logic as well. So I'll just come here and create a static variable so that it remains alive between function calls, and it's going to be of 32-bit. And I'll call it our last underscore interrupt, last interrupt time, and we'll initialize it to 0. So I'll come back here. Now, I'll create an if block here. And in this if block, we are going to perform the logic, the debounce logic. But before that, we need to get the current time. So I'll create a variable here called current time. And I'll invoke this function called get tick. Now, inside here, we can perform the debounce logic. So we need that it should only execute if the last press was more than 200 seconds. So to do that, we are going to say if current time minus the last interrupt time is greater than 200, then you toggle the LED, update the timestamp. So I'll have here last interrupt time is equal to current time. So this is it. I think now our code is fine and it should work. So if you are asking why are we using the debound? So the software debound that we have created is because mechanical buttons are dirty signal. And when you press them, the metal plates vibrate. Therefore, it's going to create a tiny zeros and ones or the on and off signal in a few milliseconds. So without debouncing, the LED would toggle like 5 to 10 times in a microsecond, appearing either off or flickery. So to avoid that, we use the debounce. So with debounce, we are going to check the current time minus last time should be greater than 200. So this code that we have written here, we tell the STM32 that if you just respond to a press less than 200 millisecond ago, then ignore this one, and it is probably just a bounce. So that's it. So now we can debug our project. So I'll just click here to debug. Okay, we're getting an error that says, oh, last interrupt time defined but not used. So I'll just check the variables. I think everything is set correct here. Okay, I think the problem is here. We don't need this comma here, so we can debug it once more. Okay, it's built successful, so we can now run the project. Okay, okay, the program is successfully flashed to the microcontroller, so now we can give it a test. So I'll just click on the button, and you should see. So that's it about the video, guys. If you like it, share it with your friends. Kindly subscribe. Peace.